Okay, so here we're going to be doing some practice, doing volumes of revolution using vertical slicing, and we'll be looking at the first method, which is disks. So for this example, we'll be looking at the volume of a sphere. And we're going to show that the volume of a sphere with a given radius of capital R is of course given by 4/3 pi r cubed. Okay, so this is a familiar formula to us, and we're just going to verify this formula using calculus. And so what we know from last time is that if we would like to do a volume, what we will do is we'll be integrating the surface area of our cross-sectional cuts, and we will be doing vertical cross-sectional cuts, so we will be working here with delta x, and then what we will need to find is the smallest value and the largest value of x on our region to be the limits of integration. So to begin with, if we would like to generate here a sphere, there are a few different ways of doing so, but one way is to start with a semicircle, and we're going to start with a semicircle here that is just sort of the upper half of the circle, and we know that it has a radius of capital R, so we have over here minus R and here positive R. Now, to use this in generating the complete sphere, what we'll do is we'll take this two-dimensional region and we'll rotate it around the x-axis. And in doing so, we will complete the sphere. Okay? And then what we'll look at doing is a vertical cut. So if this is our sphere, we would like to do a vertical cut through the sphere, which would look something like this. And we know that the thickness of our cut, because it is vertical cut, would be delta x, and that would be our vertical cross-sectional cut. So if we remove that and we look at that cross-sectional cut, what we end up with is simply a disk, and we know that this disk, being a vertical cut, has a thickness of delta x. Now, we would like to figure out what is going to be the surface area of this cross-sectional cut, and so knowing that it's a disk, all that we end up needing to do is figure out what is going to be the radius, because we know once we have the radius, the volume will be given by integrating pi r squared. And so looking back at our curve, what is going to be our radius? Well, our radius is actually here just the distance from the outside of our disk to the axis of rotation. And so looking at this picture, we have that is our radius. And so really, if we look at this point on our starting curve, then we are interested in the y value being the distance from this point down to the x-axis. And so what is the y value there? Well, if you look at this starting curve, what was the equation there? And we know that it was a circle with a radius of capital R. So that upper half of the semicircle there is just going to be the square root of r squared minus x squared. And so that is going to be the y value of this point. And that y value will be our radius. So this radius here is actually just going to be the square root of r squared minus x squared, and that's the y value. So we can go back now and plug everything in, and we do end up with pi. We have our radius is the square root r squared minus x squared. We know our lower limit of integration, the smallest x value that we're looking at right here is negative r. Largest x value over here is capital R. And so now we can integrate this, which I almost forgot. This is our radius. This is going to be squared. And so we end up getting the integral really of just r squared minus x squared from minus r to r. And so now all we have to do is integrate this. First, what is the antiderivative of r squared? So this you do need to remember for sure. What is capital R? And capital R is actually just a constant And so the antiderivative will just be r squared multiplied by x. Okay? Then we go here, we do the antiderivative of x squared. That's going to be x to the power of 3 divided by 3. That's our antiderivative, and now we would like to evaluate it from minus r to r. And so here we use FTC2, we'll plug everything in. We end up with pi multiplied by r squared. We plug in our upper limit of integration for x everywhere. And then what we're going to do is subtract what we get when we plug in our lower limit of integration, which is negative r. And then we have a little bit of algebra to do. So we're going to simplify this. And we get r to the power of 3 minus 1/3 r to the power of 3 minus, here we have negative r to the power of 3. Here, this is negative r to the power of 3. It's still going to be negative. However, here we end up with a double negative, and then we have another one over here, so we get actually just minus 1/3 r to the power of 3. And now we're going to simplify this whole thing altogether. And so what we end up with is pi. Oh, this is actually going to be positive. So here we did have this double negative. And so now, after fixing that, we put everything together. We get 2r cubed, putting this together with this, minus 2/3 r to the power of 3. And so what we end up with is pi multiplied by 6 minus 2/3 r to the power of 3. And this is, of course, what we're looking at. This is going to give us our pi times 4/3 r to the power of 3. And that is it.